So after we now discussed the very general reaction mechanism for electrophilic addition reactions, we want to continue with a more detailed look on the different addition reactions, and we will start with the addition of halogen halides. This reaction is a two-step reaction, and the reactivity is dependent on the used halogen. So we have the first step where the carbon-carbon double bond will act as nucleophile, and it is attracted by the partially positively charged hydrogen atom, which is induced by the difference in electronegativity between hydrogen and halogen. And this is the first step, which is the slow step. Here we create an intermediate planar carbocation, and the halide is went out of the molecule. However, it is still very close to this carbocation. And then in the second step, which is a much faster step, we will see attack of this halide ion to the carbocation. And as we know, the carbocation is planar. That means, in principle, the halide ion can either attack from above or from below, and there is no specific preference. That means we will end up with a racemic mixture of halogen alkane. And important to know is that this reaction is an exothermic reaction because the newly formed carbon-hydrogen and carbon-halogen bond is stronger than the two broken bonds, which are carbon-carbon pi bond and hydrogen-halogen sigma bond. If we want to have a deeper look into this reaction mechanism, we can look at orbital overlap, and we see here the alkene, which has a filled pi orbital of the carbon-carbon double bond. This is the nucleophile, let's say, and then we see an empty sigma star orbital of the hydrogen-halogen bond, and here is the first step, this nucleophilic attack. And then we have this intermediate carbocation where we see that the sigma orbital of the newly formed carbon-hydrogen bond is filled, and on the carbon atom of the carbocation we have an empty p orbital. And here we can have an end-on overlap of this empty p orbital with the approaching halide ion, and then we will end up with this newly formed alkene. And important to see here is that we have now a filled sigma orbital of this new carbon-halogen bond. So overall, we can say there is a kind of rearrangement from the carbon-carbon pi orbital towards two sigma orbitals, which are now in the carbon-hydrogen and carbon-halogen bond. And what is also important to know is that the addition of an halogen halide is regioselective. That means if we start with a terminal alkene here, we would have two possibilities on how to form the carbocation. And here you can see the two possibilities. So first of all, we can have the secondary carbocation, and then we can also think about producing a primary carbocation. Then we should consider which effects are there, and for the secondary carbocation, we can see that the R groups here have two plus I groups, so that means the electron density will be pushed towards this positive charge, and therefore the secondary carbocation is stabilized. And if we compare it with this primary carbocation, we only have one R group. That means we have only one plus I effect, and therefore the carbocation is less stable. And of course, we then go for the more stable carbocation, and in the next step, the nucleophile will attack this positive charge, and we form then very selective the secondary halogen alkane, and we do not see the primary halogen alkane. And the reason for this is that the secondary carbocation is more stable than the primary carbocation. So, in summary, we can say that the addition of an halogen halide to a terminal alkene will end up with the secondary halogenoalkane. And in general, the reduced selectivity can be explained by the so-called Markovnikov rule. And the Markovnikov rule says, on addition of halogen halides to an alkene, hydrogen will be attached to the carbon with the fewest alkyl groups, and the halide will be attached to the carbon with the most alkyl groups. And therefore, the stability of the intermediate carbocations will determine the final product formation. And we can say that this reaction is regioselective. That means we selectively form only one structural isomer.